in this class we will see some aspects of solving the dual. I will also introduce some matrix notation more in tune with solving this problem, and also to introduce the matrix way of solving linear programming problems. Now again we go back to the familiar problem where we maximize 10x1 plus 9x2 subject to 3x1 plus 3x2 is greater than or equal to less than or equal to 21 and 4x1 plus 3x2 less than or equal to 24. We already know that the optimum solution is x1 equal to 3, x2 equal to 4 with z equal to 66. Now here is the dual which we have seen, and we know that the optimum solution to the dual is y1 equal to 2, y2 equal to 1 with w equal to 66. Now let us introduce some matrix notation. Just to show this, there are one can spend a lot more time starting from the beginning, but let us just see a little bit of the matrix method. Now let us assume that I am solving for x1 and x2. x1 and x2 forms what is called basis, forms xb, which is a set of basic variables. The set of basic variables is called basis. Let us say x1 x2 is now the set of basic variables. So if we are solving for any xb, then if you remember doing some matrix methods of solving equations, then the solution to equations is given as xb is A inverse b, where A is the coefficient matrix. In our case we use the notation capital B, so xb is equal to B inverse b. Now the solution, if I know the basic variables in the primal, if I know the basic variables that I am solving for, then xb is equal to B inverse b. I will tell you what capital B matrix is and its inverse. The corresponding solution to the dual for the given basis is given by CB B inverse, CB B inverse. Let me show all this computation by treating x1 and x2 as our basic variables. So xb is x1 x2. Now this capital B is called the basis matrix whose inverse I am marking. The capital B is the basis. Now what is the basis? The basis is if x1 and x2 are the basic variables, the coefficients of x1 3 and 4, now 3 and 4 will come as the first column of B. x2 is the second basic variable, and remember there are two equations, therefore we can solve only for two basic variables. So x2 is the second basic variable, 3 and 3 are here, so 3 and 3 is also here. That is your matrix B. So this is your matrix B. So B is given by this. So this inverse, B inverse, so B inverse B, the small b which is shown here, small b is the right hand side, small b is your right hand side. So now what you can do is, you can take this, invert this, multiply with the right hand side. Now you could have done some methods for matrix inversion. The first method that you would have learned to invert a matrix is to find the determinant and the cofactor and the adjoint, and adjoint B by determinant B is B inverse. Now B inverse is inverse matrix for a given square matrix with a non-zero determinant. So if B is the given square matrix, B inverse is another square matrix of the same size such that B into B inverse or B cross B inverse is I, B inverse cross B is also equal to I. So that is the definition of B inverse. So you could find the determinant, the cofactor and the adjoint, and if you did that, your B inverse matrix will look like this. This is your B inverse matrix. Now B inverse into B, right hand side 21, 24 will give you through matrix multiplication minus 1 into 21 plus 1 into 24 which is 3, and 4 by 3 into 21 which is 28 minus 1 into 24 is 4. So the solution is x1 equal to 3, x2 equal to 4, which is your optimum solution, for the basis x1 x2. Now what is the value of the dual? Here by solving the dual we got this solution. By solving the dual optimally we got y1 equal to 2, y2 equal to 1. Now the dual is given by CB B inverse. What is CB? CB is the objective function coefficient for xb. So objective function coefficient for x1 x2 is 10 and 9. So CB is 10 and 9. B inverse is the same B inverse. You could get B inverted to get this. And now when we do the matrix multiplication, 10 into minus 1 plus 9 into 4 by 3, 9 into 4 by 3 is 36 by 3 which is 12, minus 10 plus 12 is 2, and 10 into 1 plus 9 into minus 1 is 1. So the optimum solution to the dual is 2 and 1 with y1 equal to 2, y2 equal to 1, which is y1 equal to 2 and y2 equal to 1. So we could do this. In fact, it is also possible to show that simplex does exactly that, and we will see how simplex does exactly that. So we now go back to show this is the simplex table, and then we realize that x1 x2 are shown the other way, x1 x2 are shown the other way, and now we realize x1 equal to 3, x2 equal to 4, y1 equal to 2, y2 equal to 1, and then we realize that since we did x1 x2, now the B inverse that we calculated from here is minus 1 4 by 3 1 minus 1, and now you realize it is minus 1 4 by 3 1 minus 1. It is shown the other way, the reason being x2 is coming first. If I had taken x2 x1 as basis, which means if I had started with 3 3 3 4, then the B inverse would be here. Since I started with 3 4 3 3, the B inverse, first column of B inverse is here and the second column of B inverse is here. Now we can also, we already know that the primal solution is shown here, the primal solution is shown here, and the dual solution is shown here. Now we also know that this primal solution is B inverse B, and we can also show that this dual solution is CB B inverse. Now in the previous slide I had multiplied with 10 and 9 because I had taken x1 first and x2 second. If I take x2 first and x1 second, I will multiply with 9 and 10, which is what we actually did. CB B inverse. If you see this value, the negative will be 0 minus 9 into 4 by 3, 10 into minus 1. So this is one column of the B inverse multiplied by CB we got here. This is other column of the B inverse multiplied by CB we got here. So what simplex does is, simplex does B inverse B and CB B inverse through our row column operations. Therefore we are able to see the solution to the primal as well as solution to the dual in the simplex table. We are able to see as the negative of the Cj minus Zj. Now let us take another example and see how we can show this. Now let us take the minimization problem that we saw very early here when we did the simplex algorithm. The problem is to minimize 7x1 plus 5x2 subject to x1 plus x2 greater than or equal to 4, 5x1 plus 2x2 greater than or equal to 10, x1 x2 greater than or equal to 0. Once again, if x1 x2 are the basis, if x1 x2 happen to be the basis, then the B matrix xb is B inverse B, then the B matrix are the columns corresponding to the basis. So x1 x2 in that order, so 1 and 5, 1 and 2, so I have written 1 and 5 and I have written 1 and 2. Now we have to invert this. Once again we have to find the determinant, cofactor adjoint, or any other way to invert this matrix. Determinant is 2 minus 5 is minus 3 and so on. So if we calculate the determinant, we will get B inverse. If we calculate the inverse, we will get B inverse this way. So, x is equal to B inverse B. So, this multiplied by the right hand side 410 would give us minus 2 by 3 into 4 plus 10 by 3. So, minus 8 by 3 plus 10 by 3 is 2 by 3, and 5 by 3 into 4 20 by 3 minus 1 by 3 into 10 by 3 is 10 by 3. So, this is the solution to the primal. Solution to the dual will be CB inverse. CB is the objective function coefficient of x1 x2, which is 7 and 5. So, 7 and 5 multiplied by B inverse, minus 14 by 3 plus 25 by 3 is 11 by 3, plus 7 by 3 minus 5 by 3 is 2 by 3. Now, we see what happens to the table. When we did the big M method, we realized that the negative of the Cj minus Zj showed this. So, the negative of the Cj minus Zj showed the value here, but because we use the big M, the identity matrix is here, Now, under that, because of the big M, we had these values, whereas we have the minus of the identity matrix which is here, the minus I matrix which is here. So, it is seen under this with a negative value. So, 11 by 3 and 2 by 3. If we go back to the previous slide, we will realize that the values are 11 by 3 and 2 by 3. Now, you realize that in this slide we are able to see this 11 by 3, 2 by 3 when we use the big M method. So, this is the simplex algorithm based on the big M method. Now, we can also check the B inverse values. If you go back to the previous slide, B inverse is minus 2 by 3, 5 by 3, 1 by 3 minus 1 by 3, minus 2 by 3, 5 by 3, 1 by 3 minus 1 by 3, minus 5 by 3, 2 by 3, 1 by 3 minus 1 by 3. You can see the B inverse directly under the minus I when we do this. There is a minus multiplication which we have to carefully observe and understand that this is the B inverse. B inverse is here. In this case, B inverse is actually here. We also show, for example, that if we did the dual simplex iteration for the same problem, we again see that the primal solution is 2 by 3, 10 by 3, the dual solution is 11 by 3, 2 by 3. Eleven by 3, 2 by 3, you can see the 11 by 3, 2 by 3 happening here. The 2 by 3, 10, x1 equal to 2 by 3, x2 equal to 10 by 3. You can also see the B inverse, minus 5 by 3, 2 by 3, 1 by 3 and minus 1 by 3. You can see this. Here you see it with the negative sign, because you see minus 2 by 3, 5 by 3, whereas it was minus 5 by 3, 2 by 3. Now, that happened because x1, x2 got interchanged. I am treating here x1 first and then x2, whereas in this you realize that x2 comes first and then x1. Therefore, we got interchanged, minus 5 by 3, 2 by 3, whereas you realize that it is minus 2 by 3, 5 by 3. Therefore, what you observe is there is a minus 1 multiplication. The minus 1 multiplication comes because the dual simplex way here. So, you realize that the original thing is actually a minus matrix, but then we kept the right hand side negative by multiplying with the minus 1. So, the B inverse gets multiplied with minus 1 when we do dual simplex, and the negative of the B inverse is shown here, which we have to carefully observe whenever we are doing a dual simplex related problem. The B inverse will not be directly visible, but the negative of the B inverse will be visible, and we need to understand that aspect. This is the problem that we looked at recently, where we had 3 constraints and 2 variables. I am just showing one of the optimum solutions. Now, if we take this very carefully, if we take this as, this is a greater than equal to constraint. So, if we take the equations as minus 5x1 minus 8x2 minus 7x3 plus x5 is equal to minus 40, and if x5, x4, x1 are taken, so for x5 we would be taking this value 5 minus 7 5, for x5 we will take 0 1 0, for x4 we will take 1 0 0, for x1 we will take 3 minus 5 and 4, and if we do the B inverse of that, we will get this value, we will get this. B inverse multiplied by 30, 40, 36 would give us straight away this value, will give us this value. So, B inverse into 30, 40, 36 will give us this value. The dual is given by y, will be given by x4, x5, x6, y1, y2, y3, y3 is equal to 1 and the value will be 36, here x1 is equal to 9 and the value will be 36. So, you can look at simplex as a method that computes the B inverse for a given basis and then computes the primal solution and the dual solution in a very systematic manner, and it moves from one corner point to another, chooses the corresponding basis. Every corner point differs with one variable coming in and one variable going out, therefore it moves from one corner point to an adjacent corner point and keeps travelling these corner points till the optimum solution is found. It is always possible to find the solution of the primal as well as the solution of the dual when we do either the simplex table or the dual simplex table or a combination. When we do a dual simplex table, the B inverse, the negative of it will be shown. When we do simplex, B inverse will directly be shown. When we do the combination, wherever we have that multiplication with a minus 1, there it will become negative and it gets a little more involved. So, with this we come to an end of our discussion on duality and the dual. So, at this point one question remains. We have spent so much time in studying and understanding the dual, at the same time trying to see where the dual is in a simplex table, what is the meaning of the dual and so on. So, we have to ask another question, how is this going to help us in our learning of linear programming and operations research, and we have to look at that aspect. Now, simplex is a way by which simplex helped us explain the dual, simplex helped us understand that it is solving a primal as well as a dual, and every linear programming problem has a dual and we can solve the dual. Another way of understanding either simplex or the dual simplex is, we have a primal feasibility, we have a dual feasibility which are linked by complementary slackness. So, if we have an algorithm that maintains primal feasibility and then approaches dual feasibility and gets it, then it is optimum. If we have an algorithm that maintains dual feasibility and approaches primal feasibility and gets it, then we get the optimum. This principle we need to understand, because this principle can be used to create simplex like algorithms, algorithms that talk about primal feasibility, dual feasibility and complementary slackness, and such methods can help solve different linear programming problems, structured linear programming problems faster and better. We will now look at 2 problems in this course. We will see what is called the transportation problem and we will see the assignment problem. Both of them are essentially linear programming problems, but then we will look at different algorithms, and these algorithms to solve these problems are essentially built around the duality principle. It is built around the principle of having a primal feasible solution and searching for a corresponding dual feasible solution, or having a dual feasible solution and searching for a corresponding primal feasible solution. And if we get that, we reach the optimum to these linear programming problems. More detailed discussion on transportation problem and assignment problem we will see in the next 2 modules.